Hi everyone, welcome to Unit 12 of online course on probability distributions. In the last unit, we have discussed moments of Poisson distribution. We derived central moments and arbitrary moments of Poisson distribution. After having the values of central moments, we are in a position to identify the character of the Poisson distribution with respect to skewness and kurtosis. So, we are finding measure of skewness and kurtosis in this unit. And as you know, skewness is defined in terms of second and third central moments. So, measure of skewness is beta 1, suppose we are considering measure of skewness beta 1, and that is defined as mu 3 square divided by mu 2 power 3. So, for a Poisson random variable, we have x follows Poisson with lambda, and earlier we have derived mu 2 is equal to lambda and mu 3 is also lambda. These are the values we derived for the Poisson distribution with respect to second and third central moments. So, based on that values, beta 1, that is defined as mu 3 square divided by mu 2 cubed, and that is equal to lambda square divided by lambda cubed, and that is 1 by lambda. And we know lambda is always positive, and so if you are calculating the measure of skewness in terms of gamma 1, and gamma 1 we know it is 1 by root of beta 1, and that is the root of this square root of this one, that is 1 by root lambda. And gamma 1 is always positive as lambda is positive. So, what is the meaning of this one? That is, Poisson distribution is always positively skewed, unlike the binomial distribution. Binomial distribution may be positively skewed or negatively skewed or symmetrical according to different values of, or according to the values of p and q. That is, if p greater than q, the character of binomial distribution is something different from q less than p, and when p is equal to q, the binomial distribution is symmetrical. But in the case of Poisson distribution, it is positively skewed. So, that means the Poisson distribution, suppose, and again one more thing you can note here, for large values of lambda, that is gamma 1 we have already obtained as 1 by square root of lambda, gamma 1 is equal to 1 by square root of lambda. So, if lambda is very large, then gamma 1 tends to 0. The meaning is, when lambda is large, the Poisson distribution approaches to a symmetrical distribution, because when gamma 1 tends to 0, the distribution is always symmetrical. So, that is according to the values of the parameter lambda, the character of the Poisson distribution is something like this. If you draw the graph of the Poisson distribution for different values of lambda, see, look, this is the curve of Poisson distribution when lambda is equal to 0.5. So, when lambda is equal to 0.5, our distribution is like this. The probability curve is something like this, and lambda is 1. When lambda is equal to 1, our distribution, the probability mass function values are like this. That is, lambda is equal to 2, that is increasing, lambda is again increasing, lambda is equal to, this is like this, and lambda is equal to 3, this is like this. and lambda is equal to 6. So, I am actually giving the probability mass function values of Poisson random variable for different values of lambda. So, for different values of lambda, we have the probability mass function curve is like this. So, when lambda is large, see this is the lambda, the curve of lambda is equal to 6. So, when lambda is large, the distribution is approaching to a symmetrical character. So, why this is Poisson distribution is positively skewed? Because you know this, because Poisson distribution is bounded on the left side, because when x is the random variable value, x is actually the values are 0, 1, 2, etc. So, that means it is bounded in the left side, but the right side is, unlike the binomial distribution, right side value is fixed to n number of trials, but here the n is not fixed. So, left side is bounded, but the right side is not bounded. So, that is this, the probability values in the left side, the values of the probability mass function values exhibits something of the form of positively skewed character. And regarding the kurtosis character of the Poisson distribution, we know the measure of the kurtosis in terms of beta 2. Suppose we are discussing the measure beta 2, you know the definition is beta 2 is given by mu 4 divided by mu 2 square. If you know the fourth center moment and the second center moment, you can calculate the value of beta 2 as mu 4 divided by mu 2 square. And already we have, for a Poisson random variable, we derived the value of mu 4 earlier as 3 lambda square plus lambda. This is our fourth center moment, and of course, the second center moment is equal to lambda. So, for a Poisson random variable, x follows p lambda, the fourth center moment is derived as 3 lambda square plus lambda, and the second center moment is equal to lambda. Substitute these values in beta 2, we have lambda square, 3 lambda square plus lambda divided by lambda square, and that is simplified to 3 plus 1 by lambda. What is the meaning? The meaning is gamma 2. Suppose you are defining gamma 2 is defined as beta 2 minus 3, that is the measure of kurtosis. Another measure of kurtosis, how far this is deviated from the symmetry, is obtained by finding the value of gamma 2, and gamma 2 is equal to beta 2 minus 3, that is gamma 2 is equal to 1 by lambda, and here also gamma 2, that is 1 by lambda, where lambda is positive. So, that means it is positive, gamma 2 is positive, gamma 2 is positive. And since it is a positive valued gamma 2, the distribution we call it as leptokurtic. That is, when gamma 2 greater than 0, the distribution is classified as a leptokurtic distribution. So, Poisson distribution is always a leptokurtic distribution. And again, one thing you can note here, if gamma 2 tends to 0, that gamma 2 lambda, for large values of lambda, gamma 2 tends to 0. That is, if the gamma 2 is derived as 1 by lambda. So, when lambda is large, this gamma 2 tends to 0. So, when lambda is very large value for a Poisson distribution, if the parameter is large, gamma 2 approximated to 0, that means it exhibits the character of mesokurtic distribution. So, that means similar to something of the form of normal distribution. And here you can see here also the same graph I have mentioned in the case of skewness. Here also you just note this is the graph. So, when lambda is large, see lambda is large, this is approaching to a mesokurtic. This is more skewed when lambda, these are the more skewed distributions. Comparing the values, larger values of lambda that approaching to that exhibiting the character of something of symmetric mesocurtic type character. So, when lambda is large, the Poisson distribution approaches to the character of the mesocurtic distribution character, exhibiting mesocurtic distribution character. As the mean, that lambda means what? It is actually the mean of the distribution. So, as the mean increases, that is lambda increases, the kurtosis decreases, which means the distribution appears flatter at its peak and thinner and have the thinner tails. So, this is the character of the Poisson distribution. Since lambda is the, we consider lambda as the parameter, not only lambda is the parameter, it is a mean of the distribution. So, as the mean increases, that is lambda increases, the kurtosis decreases and exhibiting the character of the mesocurtic, and which means the distribution appears flatter at its peak and has thinner tails. So, these are the characters regarding the skewness and kurtosis of the Poisson distribution. So, again once again you just note the Poisson distribution, since lambda is greater than 0, the parameter value is lambda greater than 0, and the measure of skewness and kurtosis depending upon the value of lambda alone, and that is always the gamma 1 is positive. So, positive is skewed, and again gamma 2 is also positive, that is leptocurtic distribution. But when lambda is becoming large, there is a tendency to exhibit the symmetrical character in the case of the skewness when we are discussing the skewness character, and mesocurtic character when we are discussing the kurtosis character. So, and then now I am going to introduce a formula of Poisson distribution with regard to deriving Poisson probabilities. And you know the Poisson probabilities are obtained by this f of x. F of x is equal to e power minus lambda, lambda power x divided by x factorial. This is our Poisson probability values for different values of x. So, when x is equal to 0, 1, 2, 3, etc. So, when x is equal to 0, this value e power minus lambda. When x is equal to 1, we have e power minus lambda, lambda power 1 divided by 1 factorial. When x is equal to, it is e power minus lambda, lambda square divided by 2 factorial, etc. These are the Poisson probability values. Instead of finding Poisson probability values from this, we are going to derive, or we are introducing a formula that provides us a very convenient method of generating probability values, Poisson probability values, if we know the value e power minus lambda. E power minus lambda is our f of 0. So, the recurrence formula provides us a very convenient method of generating Poisson probabilities, and the only value we required for generating probabilities is knowing the value of lambda, and hence the e power minus lambda, that is nothing but our f of 0. So, if f of 0 is available, all other f of x values f 1, f 2, f 3 etc. values are obtained from this recurrence relation. How this recurrence relation is obtained? And we can prove that, very simple proof, that is, you are given f of x is equal to e power minus lambda, lambda power x divided by x factorial, and just find the f of x plus 1 also, that is, replace lambda x by x plus 1. So, e power minus lambda, lambda power x plus 1 divided by x plus 1 factorial. Consider the ratio between these two values, f of x plus 1 divided by f of x, and that is e power minus lambda, lambda power x plus 1 divided by x plus 1 factorial, the whole divided by f of x, that is e power minus lambda, lambda power x divided by x factorial. Substituting f of x and f of x plus 1 in this formula, you have this. And simplifying again, e power minus lambda will be cancelled, and lambda power x plus 1 and lambda power x, there remaining only one lambda in the numerator, and this x plus 1 factorial and x factorial become in the numerator, and cancelling the common factor, the remaining in the denominator there will be x plus 1. So, that is our f of x plus 1 is nothing but lambda divided by x plus 1 into f x, and where our values of x are 0, 1, 2, etc. So, f of x plus 1 is equal to lambda divided by x plus 1 into f of x. Substitute x is equal to 0 here, x is equal to 0, you will get f of 1, that is lambda divided by lambda into f of 0. Okay. So, this f of 0 already we have, f of 0 we know, that is nothing but our e power minus lambda. And f of 2 you can find, f of 2 is equal to lambda divided by 2 f of 1. So, f of 1 is obtained here, substitute this value, you will get the value f 2. Similarly, you can calculate all the Poisson probabilities f 1, f 2, f 3, etc. on the basis of the recurrence relation between Poisson probabilities. And to understand this, the concept behind the recurrence relation and the application of this recurrence relation, let me give one example. That is an example for finding expected frequencies based on the Poisson distribution. Suppose you have a random experiment like this. Suppose a number of printing mistakes per page in a book of 200 pages given to you. You are given the observed frequencies, that is how the pages containing 0 mistake, pages containing 1 mistake, pages containing 2 mistakes, etc., or to pages containing 4 mistakes in a book of 200 pages. So, these are the number of mistakes 0, 1, 2, 3, 4. So, how many pages in 200 pages of book having 0 mistake? There will be 109 pages, and there will be 65 pages with 1 mistake, and 22 pages with 2 mistakes, 3 pages with 3 mistakes, and 1 page with 4 mistakes. So, this total is 200. So, this is our observed frequency. This is our observed frequency. We have an observed frequency of this phenomena, that is you are counting number of pages with mistakes 0, 1, 2, 3 and maximum 4 in a book of 200 pages. And if we are applying a theoretical model here in this phenomena, in this case suppose we are applying a theoretical model, and that theoretical model we adopt as a Poisson distribution, because this is we can apply the Poisson distribution in this model, because number of mistakes that is rarely occurring event, and 200 pages are there. So, number of trials is very large here, and probability of getting a mistake, probability of getting a page with a mistake is very small. So, we can apply the Poisson distribution model here, and to find the expected frequency, if we are applying the Poisson distribution model here, that is we are finding expected frequency out of n is equal to 200 pages. We have 200 pages. Out of this 200 pages, how many pages have without any mistake? how many pages having one mistake, how many pages have two mistakes, and how many pages where we have three printing mistakes, like this. So, we are finding the expected frequencies, and these are the observed frequencies, and we are finding expected frequencies on the assumption that this model is fitted by a Poisson distribution. So, what are the quantities we require to find the expected frequencies? We need the first of all, if we want to apply the Poisson model, we have to find the parameter of the model. What is the parameter here? The parameter of the Poisson distribution is lambda. How the lambda is obtained? Lambda is not given directly, but we know that lambda is the average value of the or a mean of the distribution. So, on the basis of the given data, you find the average value, that is, these are the given values. Based on that given value, we are finding what is the average. As usual, you know the average is obtained, this is a frequency distribution, you find the average, that is by multiplying x into fx. So, x bar, that is mean, is equal to sum of fx divided by sum of f, and sum of fx means the multiplication of these two, that is 0 into 1 plus 1 into 65 plus 2 into 25, 3 into 5 and 4 into, I think this is a mistake, this may be 5, sorry. Yeah, no, this is actually 3 itself. So, this is the mistake, this is 3 into 3. So, 0 into 109, 1 into 65, 2 into 22, 3 into 3 into plus 4 into 1. And that value, after simplifying this expression, that is equal to 200. And you know summation of f, that is total frequency, total number of pages in the book is 200. So, this is the usual method of finding arithmetic mean when you are given a frequency distribution of certain observations. So, x bar is obtained as 0.61. Now, you identify that this x bar is the average of this frequency distribution, and if we are applying Poisson distribution, average or mean is approximated to the sampled mean. That is, you can treat lambda as this 0.01, you can take the value of lambda as the 0.01. So, first of all, you find the x bar, since lambda is not given, if we are applying the Poisson distribution model to find the expected frequency, you find the parameter value, and lambda is obtained by finding the average of the observation of the frequency distribution, and average is obtained by 0.61, and that is equated to our parameter. And now, you find the Poisson probability values. What are the Poisson probability values? Lambda is equal to, already we have lambda is equal to 0.61. And now, you find f of 0, as we know for a Poisson probability value, f of 0 is equal to e power minus lambda, or other things, these are the, so that is e power minus lambda, and e power minus lambda is equal to e power minus 0.61, and that is approximated to 0.5432. So, this is our f of 0, and after getting f of 0 using the recurrence relation, it is easy to find the other probability values f1, f2, f3, f4. And what is f1? f1 is equal to, actually the recurrence relation is lambda divided by x plus 1 fx. Our recurrence relation f of x plus 1, earlier this is our recurrence relation. On the basis of this recurrence relation, you find f of 1. F of 1 is equal to lambda divided by 1 f of 0. So, lambda f of 0 is our f1. Lambda is equal to 0.61, and already we have the f of 0 value, we have this value 0.5432 and multiplying you will get the value 0.3314. So, F1 is obtained and F2, use the recurrence relation F2. F2 is what? Lambda divided by x plus 1, x plus 1 is 1 plus 1, that is 2, F1, and lambda is equal to 0.61 divided by 2. And we have already obtained F1 here. So, substitute here F1, that is 0.3314, multiplying you will get 0.1011. And F3, you find F3, that is lambda divided by 2 plus 1, that is 3, F2, and 0.61 divided by 3. And F2 value, we have F2 value already calculated, we have is that value 0.1011, that is equal to 0.0206. F4, what is F4? Lambda divided by x plus 1, that is 4. F3, 0.61 divided by 4 into 0. This is substituted here, 0. And this value. So, suppose you are given a experiment finding the printing mistakes in a book containing 200 pages, observed frequencies are given, and what we are doing? We are approximating Poisson distribution to find the expected frequencies, and to get the expected frequencies we require first of all we require the parameter of the distribution lambda, and since lambda is the mean of the distribution, we can approximate the value of the parameter based on the sample mean, and sample mean we calculated as 0.61 for the distribution, and based on the sample mean you can find the Poisson probabilities based on the recurrence relation. On the basis of the recurrence relation, it is convenient to find the Poisson probabilities. And after getting the Poisson probability values, we can find the expected frequencies. How we can find the expected frequencies? You multiply the total number of pages, that is n is equal to 200 with the corresponding probabilities. So, you multiply with this value with capital N, that is 200, you will get the expected frequency corresponding to 0. You multiply the value n with this, you will get the expected frequency corresponding to 1, like this. So, that values are, hence the expected frequencies are the value, this is obtained by n into f of x. First of all, you find the f of x value, different probability values corresponding to x 0, 1, 2, 3, 4, and multiply with n, and you will get the expected frequencies. So, number of mistakes 0, 1, 2, 3, 4 we have, and the expected frequencies by multiplying the corresponding probability values with the total n, you will get the value like this. These are the expected frequencies. We have the observed frequencies are 109, 65, 22, 3, 4 corresponding to 0, 1, 2, 3, 4, and now we obtained the expected frequencies like this 108.64, 66.27, 20.21, 4.11 and 0.63. So, these are the expected frequencies. So, here actually how we are addressing a given observation and finding the expected values. If the observed frequencies are given, how we are finding the expected frequencies based on the assumption that this can be modeled using the Poisson distribution. First we identify the parameter lambda, and in order to get the parameter lambda, you identify the sample mean and equate that sample mean to the lambda, because lambda is the mean, and find the n into f x, that is our expected frequencies. So, this is actually is part of the fitting of distribution concept, and we will discuss this type of fitting of distributions in another unit. So, with this we wind up this session. So, thank you for listening this session. Thank you.